Okay, so this is the makeup lecture. So this would be lecture, I think it's lecture teaching. Oops. Oh, it's lecture. Okay, all right. Okay, so this is lecture 16 of ECE641. So we're gonna finish up the material on map estimation today. So let me go to the document camera and I can use that to do this. Let's see, so that should be working hopefully. Okay, yes, the document camera is working. All right, and I'll hit the focus. There we go. Okay, so this is, that's the update equation. Let me see if I can focus this again. That's the update equation for the gradient descent. Okay, the camera's hunting around. What's it doing? That's really weird. I've never had this happen before. Okay, that was weird. It's done now. Okay, it's happy now, I guess. Okay, there it goes. It was having some kind of problem focusing. All right, so this is the equation for a gradient descent. That's the gradient of the function. Oh, the function we're minimizing. So f of x is equal to 1/2 y minus ax squared. So this is like least squares fitting, plus 1/2 x transpose bx. So then the gradient of f of x is equal to, I put a sigma squared here, sigma squared. So the idea there is that this sigma squared allows you to control the amount of regularization. So this is the variance in x. In other words, as sigma controls how much variation you can have in x. So then if you compute the gradient here, you get the gradient is minus 1 over sigma squared a transpose y minus ax plus bx. Okay, is that right? Oh, the sigma's in the wrong place. This is sigma squared here. Okay. All right. How come I'm getting like some odd shadows? Let's see if I can do a little better. Okay. Yeah. All right. Any questions about that? Okay. So then gradient descent x of k plus 1 equals x of k minus alpha times the gradient of f of x. It's minus because you need to roll downhill, not uphill. So the gradient tells you the uphill direction. You multiply by negative alpha. You move in the opposite direction of the gradient. Alpha is the step size. Okay. Now, so then what happens is then the update becomes x of k plus 1 is equal to, this is I minus alpha times A transpose A plus sigma squared B. Okay, this is a different alpha. This is xk plus alpha times A transpose Y. Okay, this is a different alpha because maybe I'll make this a different letter. Maybe I'll make it an omega. No, alpha is good. I'll make it alpha I'll make this alpha prime, because the relationship between this alpha and this alpha is there's a scaling factor of sigma squared. Okay, but the point is that this is just a constant you have to pick. That's a different constant, but they're related by a scaling factor. So I think alpha times 1 over sigma squared is, so alpha is equal to alpha prime times 1 over sigma squared, I think. Alpha equals alpha prime over sigma squared is the relationship. Let me see if I can autofocus this thing again. That's better. Okay, now, all right. Now, assuming that the limit as k goes to infinity of xk converges to something, it'll be k infinity. So it'll be a steady state. So if it's a steady state, then what will end up happening is the new x is equal to the old x. So the gradient at that point will be 0, right? So what will end up happening is you'll have alpha, and you'll have that x infinity is equal to I plus A transpose A plus sigma squared B times x infinity plus alpha A transpose Y. So this is assuming that it reaches a steady state. Now, if I define epsilon k equals xk minus x infinity, then this is the error in the difference. This epsilon k is the change. It's the difference between the x you have and the x you would like to have. X infinity is the x you would like to have. Xk is what you currently have. You're iterating this gradient descent. Hopefully xk converges to x infinity, and then epsilon goes to 0. So you take this thing here, and oops, sorry. This is minus, and that's plus, and what's the output is epsilon k. Okay. So if we do that, if we subtract these two equations, these two terms cancel because they're exactly the same. These terms are exactly the same, except for this is xk and that's x infinity. So you get the difference between xk and x infinity is epsilon k. And same thing here. So what you're going to get is you get that epsilon k plus 1 is equal to I plus A transpose A plus sigma squared B times x, oh, I'm sorry, epsilon k. Right, now, what you do is this. I'm going to follow the notation I have in here. Hold on. So H, you define H as equal to, I define H as A transpose A plus sigma squared B, okay? So then this thing is that epsilon k plus 1 is equal to I plus H times epsilon k, right? I messed something up. I left the alpha out. So there's an alpha here. And then this thing here is alpha H, right? This is alpha H. Oh, but it's a minus. Gosh. Let me write that again. Epsilon k plus 1 is equal to I minus alpha H times epsilon K. This is the same thing, just sloppily written. Okay. So what you can see here is you see that, so let's say, so what ends up happening is epsilon K is going to be equal to I minus alpha H to the K times epsilon of 0. So if I minus alpha H is 0, then in one iteration, this thing converges. The problem is alpha minus I minus alpha H isn't 0. If you do, let's say that the eigenvalues of this thing are distinct, and so that the matrix can be a factor. Then what ends up happening is you get you have that H equals E. This is actually H is a symmetric matrix, so that A transpose A is symmetric, B is symmetric. So this is a symmetric matrix. So you can always write this in this way. So this is Eigen decomposition. Okay, we're going to test a new feature of this software, if I can figure out how to use it. I'll put up chat. Okay, how many people have read the notes? Can you put up your hands? How do you put up your hands? Do you guys know how to put up your hands? Is anyone listening to me by any chance? Yes, good job. Okay, everybody who figures out how to put up their hands gets an A. Or something. There you go. So everybody's read the notes? Okay, read the notes. If you haven't read the notes, read the notes. Okay. So that's the Eigen decomposition. So what ends up happening is that I can substitute that in. Now, so what I get is this. I get that I minus alpha H is equal to E times I minus alpha lambda E transpose. Does anybody, do people understand why that's true? Because E transpose is the identity. That's why. Okay. So if I plug this in, then what happens is I get, if I define E tilde as of K as E transpose times E of K, then this is just the rotated error. Why do I call it a rotated error? Because E transpose here is an orthonormal rotation matrix. It's an orthonormal matrix, which means it's essentially rotation. So this is just a rotated error vector. The norm of this vector has to equal the norm of this vector because that's a rigid body rotation. So rigid body rotations preserve length, right? So if I do that, then I get the following. I get that epsilon tilde K is equal to lambda to the K times epsilon tilde 0. But this is diagonal. So that means that if you look at the individual components of this epsilon, so let's say N, or maybe I is a better letter. This is going to be equal to lambda I to the K times epsilon 0I. So each component, okay, each component, this is like 0, this is I, this is N, this is K, this is time, iteration number, iteration number, it decays, hopefully, exponentially, right? And the this is k, and it decays at rate lambda I to the k. Now, it's only going to decay if lambda I is less than 1. If it's greater than 1, then this is actually going to blow up, okay? But it'll decay if it's less than 1. So what's lambda I? Well, lambda I, okay? So lambda, oh, hold on for a second. Oh no, you guys have got to stop letting me do stupid things. This is I minus alpha to the k. So this is 1 minus alpha to the II. Shoot. This is 1 minus alpha to the k. So oh, shoot. This is if the absolute value of 1 minus alpha lambda II is less than 1. So the thing is this, okay? You'd really like, what is this? This is 1 minus alpha lambda II. This is the eigenvalue of H. Remember H was this thing, okay? H was this, oh, where was it defined? H was defined here. H is A transpose A plus sigma squared B. So that's H. So the convergence of gradient descent depends upon the eigenvalues of this matrix, okay? In particular, you want 1 minus alpha times those eigenvalues to be approximately equal to 0. This is what you would like. The problem is you can't make them all equal to 0 at the same time. The problem is this. So let's say you have, this is lambda II. So II is the dimensionality of lambda. So it's the size of the image you're trying to reconstruct, okay? Well, so let's say that some of these values are very close to 0, and some of them are maybe large. So you might have something like this. Okay, so those are the eigenvalues. Well, what will happen is that, so now you have 1 minus alpha times lambda II. This is n, where n is the dimension. So what will happen is that you would have 1, but instead of you're subtracting something, so you get something like this. Right? It looks like that. This is close to 1. That is good. That's close to 0. This is good. This is bad. Why is this bad? Because this number here is almost 1. So every time you multiply, when you take high powers of that, the convergence is going to be very slow. So the problem with gradient descent is that you can't set a value of the step size, which is good, all the time. Now, you might say, well, okay, I'll just crank alpha up so that for these small eigenvalues, I get rapid convergence. But if you crank it up too high, what will happen is eventually this will come down like this, and this is 1. This will diverge. Because there, the magnitude of 1 minus alpha lambda, it will actually be negative. I mean, less than 1. Its magnitude will greater than 1. So the thing will oscillate and diverge. So the problem with gradient descent is you can't set a value which is good all the time. Okay, that there's no good value of the step size. Like it won't work in both cases. So here it's what the basic idea. Usually, what you do is you set the step size to be 1 over the largest eigenvalue. Okay, and because then that ensures the fact that your convergence at the largest eigenvalue is fast. But then what will end up happening at the small eigenvalues, the convergence will be slow. And if you try to crank it up, the thing will oscillate. So you have to read this, okay? This is the best I can do as far as explaining it. But if you go through this very carefully, hopefully it'll become clearer, okay? And what ends up happening is, so you can't get good convergence at low and high frequencies. These eigenvalues represent low and high frequencies, usually in your problems. So typically, gradient descent will converge rapidly at low frequencies, but not at high frequencies. And the reason is that usually this A matrix will measure the low frequencies well, but maybe not the high frequencies well. Not always, sometimes it could be some other kind of sensor, but for most typical sensors, they're good at low frequencies and not high frequencies. So then you get slow convergence at the high frequencies. Okay, now, let's see, okay, frequency, okay. Now, frequency analysis of gradient descent. I kind of feel like you guys have to read some of this yourself because I'm basically running out of time. Iterative coordinate descent. Okay, iterative coordinate descent. This is different. So iterative coordinate descent is different. In iterative coordinate descent, the idea is that you pick one pixel at a time. So you have one pixel. Yep, this is the image. You take one pixel. The value, the image associated with just that one pixel being on, I write as what? I write it as E sub epsilon sub s. So that's equal to, it's a vector. Oh, it's a vector. It has all zeros in it except for a 1 in one location. And that location is at position S. So it's like an impulse at position, at pixel S. Okay, so that becomes your direction vector. So D is equal to epsilon S. And the idea is this, okay? Okay, I like to describe coordinate descent this way. So you have a bunch of knobs on some device, okay? And then this device has a meter on it, right? So you have a little needle here, okay? And your goal is to get that needle to go to a maximum position. So, and you want to turn these little knobs here in order to get this needle maximum, okay? Now, you know, gradient descent, the idea in gradient descent is not very human kind of thing. Humans very naturally do coordinate descent, okay? So in gradient descent, the idea is you get all the knobs and you try to turn them simultaneously to maximize the position of the needle. I mean, that's just not very intuitive. I mean, how am I going to turn all these knobs at the same time? What humans do when they try to solve a problem like this is they grab one knob and they turn the knob and they try to maximize the needle position. Then they go to the next knob and they turn it and they try to maximize the needle position. And then they keep going. You may not necessarily even go through them in order. Maybe you go over to here and you turn this one until you maximize the position. And you go to this one. But you eventually get through all of them and you maximize the position of the needle with respect to each knob. Then when you're finished going through every knob, guess what? You have to go back again to the beginning. Why? Because when you adjusted this knob over here, it may have changed the best position for that knob. This algorithm is called coordinate descent, okay? Because you're maximizing with respect to each of these knobs represents a coordinate in your vector, and you're maximizing with respect to each coordinate in sequence, and then you go back and re-maximize. It's actually a special case of a broader class of algorithms called alternating descent, okay? In alternating descent, the idea is you hold some variables constant, and then you maximize with respect to the other variables, then you swap around. But the key idea here is that when you change the one variable to maximize it, you're constraining all the other ones to stay constant. So when you get finished, you have to go back and repeat. Okay. Now, coordinate descent optimization, you're going to implement this, I think, in the labs. Okay. And so I'm kind of running out of time because I feel like probably took a little bit longer than we could have on this section. So I'm going to ask that you read the notes, okay? Read the notes. So, but let me just kind of go through it. The idea in coordinate descent optimization is that you replace one pixel with the value of the pixel that maximizes, or in this case, minimizes the overall function, okay? So in this case, the direction is D equals epsilon s. Epsilon s is a vector which is 1 in the position of the sth pixel. Okay. And then alpha is a scalar that modulates that vector. So you now want to minimize over alpha. So this is a line search. Okay. Does everybody know what a line search is? Okay. And obviously, this isn't a super interactive environment. Okay, so then you minimize. Now, how you go about doing that minimization? If it's a quadratic optimization problem, you just take the derivative with respect to alpha and you set it equal to 0. And when you do it, this is the expression you get. Now, let's think about what that expression means. So the idea is that we're calculating now what the update of 1 pixel is, where 1 pixel is like analogous to one of these knobs on this instrument that you're minimizing with respect to. Okay, so so this is the solution. A star. Hold on. A star S. This is the sth column of A. That's what it means. So that's the sth column of A. And so here, yeah, I don't know. So this is the optimal value of alpha. You know what? So this is the error, okay? Epsilon here is y minus ax. That comes up a lot. So this is, y is what you measured. Ax is what you should have measured if x is your solution. So this is the difference between what you measured and what you should have measured. So I'm calling it epsilon. And that's how it works. If you expand this term B is the covariance matrix, the precision matrix associated with the it's the precision matrix associated with the prior distribution on the image. And remember, B here is equal to 1 over sigma x squared I minus g. Right, so it's going to turn out that B of B. Oh, we don't even need the x squared because it's already built in. Oh no, it's not built in. Right. So hold on. I have to look at this expression a little more carefully. XS minus lambda. Oh, lambda here is defined as sigma over sigma x squared. That's a little tricky thing I did there. So B here, ij, is equal to 1 over sigma x squared times, this is 1, no, it's delta ij minus gi minus j, assuming that we have this is the non-causal predictor. So let's look at this expression. So this is, if you take alpha and you plug in the expression for alpha for the update, this is what you get, that the new pixel is equal to the old value of the pixel plus this expression. So let's look at that a little bit. this thing here, that's the error back propagated to the pixel, okay? Then, okay, don't worry about that. This expression here, the difference between x and this is the non-causal prediction of x, and that's x. So the difference between them is the non-causal prediction error. So if the image is smooth, then this non-causal prediction error would be 0, and that term wouldn't even matter, okay? If the image is not smooth, this will force x to become smaller so that, let's say the XS here is larger than its predicted value, it'll drive XS down so that XS will then be smoother, okay? So this causes the reconstruction to be smooth. This causes the reconstruction to match the data. And you're going to implement this when you do the lab, I think, okay? 9, okay, so now, there's one other very important trick, okay? This is the computation it takes to do, one pixel update. But you need to update every pixel in the image. Remember, this is like, the pixels in the image are like this knob on this amplifier, so this thingamajiggy. So you have to go through, you have to maximize with respect to each one, and then you have to go back and restart. So you have to update every pixel in the image, and then you have to go back and re-update every pixel in the image. So one update of every pixel in the image is generally considered a single iteration of coordinate set, even though technically speaking, a single update of a pixel is an update. But normally people consider one update of every pixel to be a full update of the image. And so the problem is this: the computation for this update is expensive because you have to take the inner product between this is the size of the whole image, and you have to take it and multiply, you have to multiply 2 images together. So if your image has n pixels in it, this thing is at least of order n. And actually, you have to do this forward projection of A. So that's going to be, okay, the forward projection of A. Okay, so this is an important issue too. I guess I may as well explain it right now. That A is usually sparse. Okay. A is usually sparse. Okay, by sparse, I mean that it has mostly zeros in it. Wow, this thing here is, I don't know, I'm not totally happy with this projector today. I guess I have to get used to using it again. It's been a while. I'm not, maybe that's the problem. Okay, that's better. Okay, A is usually sparse, okay? So let me see if this helps. That helps, maybe a little bit. Okay, A is usually sparse, which means it's mostly zeros. Also, the sun's going down, so it's changing the lighting, I think. Oh God, this is horrible. Is that better? Okay, so it's mostly zeros. So the number, A here is m by n. So it's m by n. So this dimension here is n, and this dimension here is m. M is the number of outputs, n is the number of inputs. So the number of non-zero elements in A is equal to the number n times m0. times n. So, so M0, so basically the way to think of it is that M0 is equal to number of non-zero elements divided by n. So the other way of thinking is M0 is equal to average number of non-zero elements per row. Yeah, per column. So in a lot of applications, so M0 might be, if you had a filter, so an example here, if you have a filter and the filter is 3 by 3, then M0 is equal to what? 9, because there's 9 non-zero elements per input pixel. Okay, so so the bottom line is this. So computation. Okay, so the problem is this: the computation of doing this is too high. The computation of doing this is too high, and so the trick is you need to keep a state vector. So so you don't have to. And the problem is you have to keep redoing this a times x, which is kind of wasted computation. So there's a trick to doing it fast, and this is the trick. You compute this error vector. You keep this error vector, which is y minus ax. So this is important trick. When you go to do the labs, it's very important to do this, or the thing won't be really slow. So so here then you just have to take E transpose times A. But now the problem is that when you make the update of the pixel, you got to correct this. The value of the error, this error vector changes, so you have to update it. So you have to do this update step, okay? I'm gonna let you read this carefully, okay? Because I can spend endless amounts of time on this, and I'm not sure it would actually make it a whole lot clearer. Okay, so I think actually what I'm mostly gonna expect you to do is, hold on. What I'm mostly gonna expect you to do is read the notes at this point. You've got to read this section because, you know what, I can go through this stuff, but it'll take forever, and I'm not sure it's going to make it much clearer. I really kind of want to go on to the next section, which is non-Gaussian. So we're doing the quadratic problem. The problem is that we're doing the quadratic problem, but the problem is that the quadratic model is not so good because quadratic minimum mean square error estimation leads to a linear solution. Okay, when the model is Gaussian, but real images are not Gaussian. Real images are not Gaussian because they have sharp edges in them. As a matter of fact, if you take, let me screen share. So let's say you have an image like this, okay, and you take you know, adjacent pixels. So this is delta S is equal to delta S1, S2 is equal to x of S1, S2 minus x of S1 minus 1, S2. So this computes the difference in the horizontal direction. So this is like a horizontal derivative. And if you do a histogram, for a typical image, you know what this is going to look like? The distribution, it's going to look like this. Does that look Gaussian? No. It doesn't look Gaussian. This is heavy-tailed. Okay. So why is that? Why do you have such heavy tails? You have heavy tails because images have like edges in them. So you have like a tree, like this, the sun. It's got edges across occluding things, okay? Like along the edge of this tree, right? And that causes big jump discontinuities that create heavy tails. The images are not Gaussian. So using quadratic models, you just get blurry images. So quadratic regularization. Okay, this is really important, so I'll make it big. Quadratic regularization, okay, is equivalent to Gaussian prior, and that's equivalent to linear estimate, which is what we got in the last section. We got a linear estimate, and all these result in a blurry image, okay? It all results in a blurry image. How many people want blurry images? Nobody wants blurry images, okay? Not good. So we gotta have to do something that doesn't result in blurry images, okay? So that's why we're gonna have Gaussian Markov random fields, okay? So Gaussian is gonna be the generalization of the quadratic case, okay? So now, all right, now, so how does this work? One of the most important, okay, in my opinion, this is the quadratic, this is a Gaussian distribution over here, right? So one of the things that, is key to understanding the non-quadratic case is this identity right here, which is really a cool little identity, okay? That, let's say that, okay, how do I put this? So B here is a matrix, okay? B is a matrix. This is the precision matrix. And you can always rewrite, for any matrix B, you can rewrite this quadratic form in this expression right here, okay? Where you take the difference between pixels. So this is the difference between XS and XR. You square it and you weight it by this coefficient here, BSR. And BSR is the negative of the entries of this B, okay? But you have to remember to put the 1/2 in there. Now, there's a homework problem. You're supposed to show this is true, okay? And now, there's a second term here associated with this A, but often this term here is 0 for the applications that we use. But you can include it. The reason it's 0 is because usually what ends up happening is that the rows of B and the columns of B sum to 0 because the prediction coefficients sum to 1 in typical cases, okay? All right, so you can take this quadratic form and you can rewrite it in this following way. And in typical situations, what ends up happening is typically, what ends up happening is that AS is equal to the sum over R of BSR is equal to 0. Okay, so in that case, X transpose BX is equal to the sum over S and R of BSR XS minus XR squared. Okay. Okay, where this is sum over all unique pairs. So here's the thing. So when you're summing over the pixels, and when you sum over this matrix, you have the sum over S, the sum over R. So this is X transpose BX is equal to sum over R of XS times BSR XR. Now, when you sum over this, you sum over every value of S and every value of R. B is the symmetric matrix, so BSR is equal to BRS. So what ends up happening is you sum over each of these terms twice, except for on the diagonal. Here you're assuming you're only summing over each term once. Consequently, you lose a factor of 1/2, because there's a factor of 1/2 here, right? But here you're summing over each, you're summing over every S and every R, so that means each of these terms here appears twice. So because each term appears twice, you divide by 1/2. If you sum over each term once, then you don't have to sum over 1/2, okay? So, fine, so good. So that's the thing. So the general form, of the regularization for a quadratic prior distribution is this form. Okay, this is a general form. The only thing we're assuming here is that the A's, S's are 0. But the reason we assume the A's are 0 is why? Because usually what ends up happening is you take, so you have, if you remember the non-causal prediction filter, GS, it typically, you'd have like delta S minus R times, oh, hold on. The non-causal prediction filter is going to be G of, say, N minus, delta N minus G of N, right? So it'll be something like, there'll be a 1 here at N equals 0. And then here, there'll be a minus 1/2 and a minus 1/2. Okay, and so that these two things compute the average. So this is, so you have that X of N minus 1/2 X of N minus 1 plus X of N plus 1, right? That's the prediction error, epsilon N. So in this case, the sum of these two things sum to 1. So because they sum to 1, this A is 0, and that makes you, allows you to drop that term. Okay, so the general form that we consider is P of X is equal to 1 over Z exponential of minus the sum over all S and R, right, of BSR XS minus XR squared over 2. Okay. Okay, so that's the general form. So the idea here is that in a typical say the BSR is only sums over the neighbors, is not equal to 0 only for neighbors. Okay. So what this thing does is, if you have a pixel here, these are its neighbors, there's a term associated with every pair of pixels. So this is XS, this is XR, and the difference is XS minus XR. So this term here, this penalizes large differences between neighbors. So if the neighboring pixels have very different values, then this applies a very large penalty to the difference between those neighboring pixels. Because as that difference becomes larger, then the B's here are typically positive. So then this quantity becomes large. So then the probability becomes smaller. So this penalizes large differences between pixels. Now, if it's a quadratic distribution like this, because it's squared, then this is a Gaussian. But what we'd like to do is generalize this so it's not Gaussian, right? So what we do is we put a different function in here. So the non-Gaussian generalization is this. You have P of X is equal to 1 over Z exponential of minus the sum over SR. These have to be neighbors. Of course, you can define any neighborhood you want. BSR rho of XS minus XR. And this thing is called the potential function. Okay, and then the trick becomes to pick a function rho, which is good at preserving edges, but also smoothing smooth regions. Because, okay, so we'll talk about that next time in a lot more detail. But the idea is a typical rho, so that you have here quadratic. So we have rho of delta, and then we have rho prime of delta. This is called the influence function. This is potential, and this is influence. Okay, so the quadratic here looks like this. This is delta squared. And the influence function looks like this. So the influence function tells you how much influence a pixel has on its neighbors. And this says that the effect of the influence of a function is unbounded because this function just goes to infinity, right? And the derivative here, this is actually over 2, and then this is delta. Okay, and this corresponds to Gaussian. Another possibility is a thing called Huber. Huber does something like this. This is quadratic, and then this is straight. Quadratic, and this is straight. And then the influence function looks like this. It's like this, and then it goes like this. Okay. Here, what ends up happening is that the influence is bounded. So, so what ends up happening, this value here lets edges form because you can have differences between neighbors that are large, okay? And then we'll talk about some more of these functions. There's a bunch of these functions listed. Oh, here's the broken spring model. Here are some different functions. Okay, so this is the broken spring model. Here, when the difference between pixels becomes too large, you just cause the influence to go to 0, okay? And blah, blah, blah. Then there's this argument that you really want to use convex potential functions because convex optimization behaves better, blah, blah, blah. And here are some of the functions. We'll go over these next time in more detail, actually in class, so I can draw them. Okay, so I think with that, I'll stop here, but then what I'll do is I'll answer any questions and I'll work problems so I can get a little bit of feedback, but I'll stop the recording first. All right, thanks. Hold on, how do I stop the recording?